Great. Okay. So let's talk about the matching test that we're covering in this work. So the first task is basically let's say the trivial one, right? So when we think about matching in a more of a general context, and specifically from the NLP community, we think of, okay, I have two sentences. So here, for example, what are the best motivational videos? On the other part, we have what are some of the best motivational clips? And the idea would say, okay, whether there are semantically equivalent sentences or not. So this is the question. And in this work, we're trying to kind of look at the human perspective of these tasks. And specifically, if we envision them as labelers, which provide us labels for training our models, they are the ones that should answer these questions before we get to the training of our models. The second task would be actually more familiar to this audience, is mainly research in the database community, and it's called entity matching. And entity matching, again, it's very similar. So there are some instances of entity matching that looks just like I showed you before, but more of traditional entity matching tasks look more like this. Maybe I'll take off the mask. And then we have tuples. Sometimes in context, sometimes not. We have the schema. Sometimes sometimes we don't have it, but we have more context. And again, the main question would be to match two elements, right? So here we have two elements, more complex elements, let's say. But again, the main question is matching. The third task that we're going to cover in this work is schema matching. And when we talk about schema matching, we talk about the attributes of so more of the metadata perspective. And then usually it's more complex, mainly because of the context. So when we talk about attributes, we usually think of like more structured data, in the sense that, for example, here we have telephone, which is a sub-element of contact, which is a sub-element of invoice to, and so on. So we have more context, we have more hierarchy, and so on. But again, the main idea here is that all of these are matching tasks, right? So we have two elements, we need to say whether these two match or not. So what about humans? So again, traditionally, humans are assumed to be better at this task, and most tasks, right? So if you look at the literature, you see that humans are used as validators. So here is some algorithmic result, tell me whether are right or wrong. And more recently, when we talk about machine learning models, they are used as labelers. They are the ones that provide labels to train our models, right? Another alternative would be to surpass this need for humans, right? So we can use methods like active learning, few-shot learning to minimize our human effort in training our model, or we can use even unsupervised learning and try to skip the human in the loop at all. And then when we talk about more of a crowdsourcing perspective, then there were a few works talking about the idea of, and we actually had a very nice talk about the ability of humans to provide labels. So there are some works talking about how to identify the ones that provide us with lower quality, or actually better quality. And the main idea there, or the more common idea nowadays, is to feature engineer the behavior. And this is what we follow in this work. And if we go even a step further, we saw in literature that humans have cognitive biases, and specifically in the task of schema matching, which I referenced before. And again, part of my research in my PhD showed that if we account for this behavior in an open-ended schema matching, so our human has to match everything, not the binary, as we showed before, taking account of their behavior can help improving the performance. So in this work, we look at Boolean crowdsourcing, which is actually what you think of when you think of crowdsourcing. So we have one question, let me know what you think about this question. And we use the incognito match tool for that. It was originally designed for schema matching, but we adopted it for entity matching and text matching as well. So this is how it looks like. We have a sample panel. So here is the questions that we saw before. So we have two questions, and the participants have their decision panel, and then they can choose whether these two questions match or not, and what is the confidence for that, right? So we have two parts of this scale here. After unknown, so 50 and more, if we think of that 0 to 100 means match, less than 50 means no match. This is how it looks like for entity matching. So we have some more context. Here we have the schema information, so it's kind of a more context. And then if we look at actually this is the original incognito match design. If we think of schema matching, much more context, right? So we have the schematic that I showed before, but then we also have instances, examples, we have column types and so on. How do we model this in order to calibrate this decision? So we talk about humans giving us labels, but can we do something better than just trusting what the humans provide for us, right? So we model this very similar to like a traditional machine learning model. So we have X, the pair of elements. We have a human that provides a label. But in this context, instead of saying, okay, Y is the true label, or as Joey says here, golden standard, we look at it as a prediction. Okay, and this prediction is actually more complex than just one binary label. It has more than that. So this label is also, again, in this context, accompanied by a confidence value, and also by the time, which was shown in previous research to be a major component in decision making. So this is how a traditional approach would look like. Our human will give us a label, and then we simply use it as a label, right, to train our model. So we take an alternative approach. So we first extract features that describe the behavior of a human. Then these features can be locals. For example, the confidence that was provided, they can be global. So for example, the accumulated time is a global feature. They can also be internal. Again, internal as the confidence is an internal feature. And then they can also be external. So what others think about the same question that I am answering right now. We take this representation, we plug it into a black box machine learning. A main theme here, this box should be explainable. So we should be able to say what part of the behavior actually affected the decision. And then we get our improved label. And again, much more details in the paper, the features that we use and so on. So let's look how did we do. So in our experiments, we actually used the tool that I mentioned before. So we used 300 human matchers, around 12K decisions. We performed pre-screening of these matchers and some statistics. So each decision was made around 12 seconds. If we look at the confidence, so if we just look at the confidence, maybe surprising, maybe not, but the average confidence was 0.5. But then we also implemented a smoothed confidence value. So very briefly, so if we have the scale that we saw before, if someone chose 85, they don't actually, their confidence is not actually 85. It actually scales between the 50 and this 85. So this is how we rescale it. Again, I'll be happy to talk more about that offline. So let's look at the results. We had 4 different scenarios in our experiments, so how we split the training and testing. This is like the main idea of each one. The most interesting one would be cross task and cross domain, in which we simply use like a benchmark that already exists, and then we use humans on this task to train a model, right? And this model can be used to calibrate labels that are provided for other benchmarks in the cross tasks, so a different task in the same domain. So for example, if we have a schema matching task, we use it for a different schema matching task. And in the cross domain part here is if we have a label benchmark in schema matching, can we use it for calibrating labels for entity matching? So some highlights. Not surprisingly, the lowest baseline performance was for schema matching, which is considered to be the most challenging one out of the 3. The largest improvement that we saw was for entity matching. And finally, and again, I mentioned that before, we see great potential in this cross task. So if we look at this improvement, this basically means that if we want to improve or we want to create a new benchmark, all we need to do to create like an original set of good labels, we need to take a benchmark that already exists, use some humans to train our HumanAL model, and then use it to calibrate a new benchmark that we want to use. Some final remarks. We show that using a cognitive aware feature extraction can actually generate better labels. So if someone provides us with a label, if we apply our model, we generate better labels. And we can also see that the most significant improvement, as I mentioned before, was to have a model that was pre-trained in the same domain, right? So if we have a new schema matching benchmark that we want to label, then we need to take a pre-trained model on the same domain. Some future directions, again, I'll be happy to talk more offline. So we want to explore additional features. For example, we have the mouse movements tracked. We have this data. We haven't used it yet, so we definitely want to use that. We want to, as you may saw before, schema matching has the most context, entity matching has some less, and text matching has no context. So we want to explore that by trying to see whether the context affects the decision making. And finally, we want to experiment with varying expertise levels. So a lot of people talk about domain expertise. What happens if we take like general crowd workers? What happens if we pre-screen them? What happens if we can take domain experts, researchers, and so on? So we want to explore the different expertise levels and how it affects. Yeah, that's it. And special thanks to my mentor, who is not here now, but special thanks to Alkindi, my mentor. We had a great session. I think this format is very good. So we had a great session talking about this, and thank you so much for listening. I'm happy to take questions.
Hi, thank you, Roy, for oh, yeah, it's working. Thank you, Roy. It was a very good talk. I have a question about, you show the UI when the user can see the majority vote. So you also told that you use that feature to generate the new prediction. So first, like, does it make sense to use it as a also as a feature and show it to the user? And my second question is, may it cause to confirmation bias? Like, you have a decision in mind, you're not sure, but then you see what other people think, and then you think, like, okay, if everybody thinks like that, I'm probably right. But so how does it affect to show this majority decision in the entire pipeline?
Yeah, so this is a great question because we had this in mind when we designed this framework. So the idea was to generate the most context that we can create, like our initial design. And this majority decision is actually based on initial experiments that we performed. So it's not the same majority decision that we saw before, right? So this is like an initial one. One important part of your question was that this confirmation bias. So we saw that in previous research, and it's definitely a factor. In this work, we actually build on top of the fact that everyone was provided with the same context. So in that sense, it's kind of gives us like a good comparison in that sense. But this is definitely, so as I mentioned before, one thing that we want to explore. When I say context, this is part of the context that is provided, and this is something that we want to explore. So when we design, this, each component here can be extracted. Like, we can pull it out, and one of the experiments that we want to perform is kind of playing around with this design and see what affects the different things here. And actually, this is like an original Joe Hellerstein question from Hilda 2018. So this was like gave me the idea to design it like that. So it's like a nice closure, I guess. So this is definitely something that we want to explore. Yeah.
Okay, thank you.
Thank you.
Okay, so I noticed you had time as part of your model. Does that mean that you're watching people get better, like the Bayesian inference talk we saw earlier?
This is a great question. In general, we see these labelers one time, but in this one time, they perform more than one question. And one of the features that we use in this model and we try to analyze is actually kind of the fatigue of the human, trying to figure out. So this is like the fatigue is actually the counter of what we discussed before. And for now, we didn't see like a large effect, but we didn't spend a lot of time on trying to figure out like the differences between the time period. When I say time here as a major effect is like, if you make the decision quicker, this means that usually you are more confident. And this is like back in cognitive research. So when I say time, it's actually how much time it takes
Oh,
the labeler to answer the question.
Duration, not time span.
Exactly,
Okay.
exactly. Thank you for the question.
Thank you, speaker again.
Thank you.